Hello, I'm Mr. Singleton. I'm one of the Associate Directors of Science for Outward Academy, and this lesson is all about changes of heat and specific latent heat. If you haven't already done so, please make sure you've done the lessons on specific heat capacity and internal energy, because they will be useful to know that before we start. This is the specification, so it just tells you exactly what you need to know and what this lesson is going to run through. So we're going to talk about changes of heat, what happens when you heat something, what happens to the temperature, why the temperature doesn't always increase. And we're going to talk about latent heat. And then we've got this equation here. Now this equation is given to you on the physics equation sheet. So you don't need to remember it, but you do need to be able to use it, and you need to be able to rearrange it. So we're going to look at that as well. So if you are at home doing this, then you'll just need a piece of paper that you can then pass on to your teacher when you're back in school. If you are in school doing this lesson, then you can do this on a whiteboard. I want you to tell me what internal energy is made up of. This is from the previous lesson. And what is specific heat capacity? So what does that word mean? I'll give you 2 minutes. Off you go. Okay, you got 1 more minute. Okay, so let's just go through this then. Internal energy is made up of kinetic energy and the potential energy. We're talking about the energy stored inside molecules. So remember, those gas particles have more kinetic energy than the solid particles, so therefore could have more internal energy. But it's also made up of the potential energy in there as well. Specific heat capacity is the energy needed to increase 1 kilogram of substance by 1 degree Celsius. And that was the equation that you needed to remember for that one as well. So title is changes of heat and specific latent heat. And our challenge is just to define what specific latent heat is. Our aspire is to then use that equation to calculate the change of energy when a substance is heated and its state is changed. Remember, those states are, when we talk about states of matter, it just means solid, liquid, or gas. Starter for today, I just want you to have a look at this picture on the other side of this person coming out of a bath, and I want you to write down any words that you don't understand in that text. So we've got cooling by evaporation. Do you know what evaporation means? Do we know what cooling is? And then do we know what latent heat of vaporization is? And just write those down just on your piece of paper or in your book. And when we go through them, then you can add them in. I'll give you 30 seconds. Off you go. So change of state. So when we are talking about a change of state, we're talking about a solid going into a liquid or a liquid going into a gas, or vice versa, going back down the other way. The energy needed for a substance to change its state is just called its latent heat. Okay, so that's all latent heat means. It's just the amount of energy you need to put in to change the state of that substance. And what you've got to remember, and this one's a little bit harder, is when a change of state occurs, lots of the energy going into that is actually going into the internal energy and not raising the temperature. So the temperature isn't going to change as that substance is like turning from a solid into a liquid or a liquid into a gas, because all of that energy is actually going into the internal energy, the energy store. Hard one to get around, but I want to see how much you've listened. So what is latent heat and what happens to the temperature of the water in an ice cube when it melts? 2 minutes, off you go. Okay, let's go through these answers. So latent heat is the energy needed for a substance to change its state. And what happens to the temperature of water when an ice cube when it melts? Well, the temperature stays the same. Okay, I'll let you write these in, and I'll give you 2 minutes to write in any answers that you need. If you're working at home, you could just put this straight onto a revision card if you wanted. So specific latent heat. So we've done latent heat, but specific latent heat of a substance is the amount of energy required to change the state. So this is changing the state of it. So it's gone from a solid to a liquid, liquid to a gas, of 1 kilogram of substance when there's no temperature change. So a little bit different to specific heat capacity. This is just about changing 1 kilogram of substance and not having a change in temperature. And it's still the amount of energy needed to do that. So specific latent heat of a substance, the amount of energy needed to change the state of 1 kilogram of the substance with no temperature change. I'm going to show you a couple of graphs just to help you. So here is a heating graph for a substance, and as you can see, at the bottom we're just increasing the amount of energy all the time, and on the side axis, on the y-axis here on the side, we've got temperature. So this would be going up in like 10, 20, 30, 40, 50, 60, okay, going up the side. So as you put in more energy, then at the beginning, the temperature will also increase, which seems quite obvious. If you heat a substance, the temperature increases. However, whilst it is melting, there is no temperature change at all, even though I'm putting in more energy. So I can put in more energy and I won't actually see any temperature change, and that's because that energy is being used in the internal energy. Okay, so the temperature does not change. Then when it becomes a liquid, you carry on heating it, you keep on putting energy in, and now the temperature will increase again until you get to this bit called vaporization, which is when it's turned into a gas. Okay, I'm still putting in lots of energy, but again, the temperature is not changing. And then it will turn into a gas, and the same thing then happens. The temperature increases. So that is a heating graph for a certain substance, and it's any substance. It'd be great if you want to pause this and you want to draw that down, draw that into your books or draw that onto your revision card. It just helps to explain what this specific latent heat is. Because lots of people think that as you increase the temperature, or as you put in more energy, so as you heat something on a Bunsen burner, the temperature just increases. And it doesn't. At some point, the temperature stays the same, and that's when melting is happening, or vaporization. So on this graph, what I want you to do is try to label these components. So when a solid melts and when a liquid boils, and what happens when this is happening. Just before you start doing that, you're going to put in energy, so you're increasing the internal energy, and those are used to break bonds rather than just to raise the temperature. So where is that happening? So where is the solid melting? Where is the liquid melting? And then C, the last bit, the temperature doesn't increase until all the solid melts or all the liquid boils. So I want you to label them components on that graph very quickly. So sketch a graph. You don't need to put all the latent heat of vaporization and latent heat of fusion, but you do need to put A, B, and C. So I'm going to help you out a little bit here with this graph. So you've got that solid and it's increasing in temperature. Where that flat line is, that first flat line where it actually says latent heat of fusion, that should be labeled as A. And then when you've got the next bit here where it says latent heat of vaporization, that should be B. Okay, then C, where it says the temperature doesn't increase until all the solid melts or all the liquid boils. That is at them points as well. Now, there's a couple of different terms that you need to be aware of. So specific latent heat of fusion, that is when there is a change of state from a solid to a liquid. So fusion is going from a solid to a liquid. So we don't need to talk about melting anymore. We can talk about specific latent heat of fusion. That's when there's a change of state from a solid to a liquid. Specific latent heat of vaporization is a change of state from a liquid to a vapor, or as you would have called it, a gas. And then to work this out, to work out the energy needed for a change of state, you do the mass times the specific latent heat. I'll give you a minute to write those down. Okay, so this is the equation. It is given to you in the exam, so you just need to know what the letters mean and be able to rearrange it. So the M is the mass of the substance, and the L is the specific latent heat of that substance, and the E is the energy required to change it from a solid to a liquid, or a liquid to a vapor. Okay, so M is mass again, and L is the specific latent heat, and E is the energy required. Energy is always measured in joules. The mass is measured in kilograms, and then the latent heat, specific latent heat, is just joules per kilogram. So here's an example. The latent heat of fusion of gold is 63,000 joules per kilogram. And what does that actually means? That means that if I put in 63,000 joules of energy to melt 1 kilogram of gold, it won't actually change its temperature. It will melt. Okay, so I'm going to let you have a go at this one. So lead melts at 328 degrees Celsius. I want you to find the latent heat of fusion for lead if 2,300 joules melts 0.1 kilograms and it stays at the same melting point, stays at the same temperature. So I want the latent heat. So you have the mass and you have the energy. You are going to have to rearrange this to try to work it out. Off you go. Right, let's work through this then. So you always write down the equation you're going to use. Okay, and then we're going to substitute the numbers in. So I know that we've got the energy already, which is 2,300 joules. And then I've got the mass as well, which is 0.1. And then I'm trying to work out the specific latent heat. So then, in order to rearrange this, what I would do to get rid of... Now, the way I've done this is to get rid of that 0.1 on the side that says times by L. I need to divide that by 0.1. So whatever you do to that side of the equation, you would do to the other side of the equation. So then I would do 2,300 divided by 0.1, and that would give me the latent heat, which is 23,000 joules per kilogram. So I would need to put in 23,000 joules of energy, and that will melt 1 kilogram of lead and not change its temperature. So I want you to have a look at this graph. So we're going to go back to this graph, and I want you to have a look at what you think takes more energy. Does it take more energy for the ice to melt or the water to boil? And then I want you to justify your answer using the graph. I'm going to give you 3 minutes. Off you go. Okay, so let's have a look. Which one do you think takes more energy, melting ice or boiling water? Well, what you should have is boiling the water, because you are putting in the energy for a lot longer. So it needs a lot longer for it to boil, and that's the reason. We'll just have a look on it. So it takes more energy to boil the water, and that can be shown by the amount of time it takes. So it takes a lot longer, therefore it needs a lot more energy. So some quick fire quizzes, and they get progressively harder, and I will give you 3 minutes to do these, because the last one needs a bit of calculations to it. So which statement about these units is correct? And then as a solid melts, what happens? And then there's 2 calculations. I'll give you 3 minutes. Off you go. Okay, let's have a look then. So, temperature is measured in degrees Celsius and the energy is in joules. If you're struggling, the W is watts and the K is Kelvin. So it wasn't going to be them ones. As a solid melts, the temperature stays the same because all that energy is actually going into breaking the bonds, going into the internal energy, not into increasing the temperature. And then a specific latent heat of melting for lead is 22.4 kilojoules per kilogram, and that of oxygen is 13.9 kilojoules per kilogram. This means that if a lead has a higher temperature, more energy is needed to melt lead than it is to melt oxygen, or more energy is needed to heat lead than it is to heat the same amount of oxygen by the same amount. Should have been the middle one. Didn't actually need to do a calculation in that one. And then number 4, energy equals mass times specific latent heat. If the specific latent heat of melting water is 334 kilojoules per kilogram, how much energy is needed to melt 100 grams of ice? Now look, it says 100 grams of ice. So the first thing you're going to have to do is convert that into kilograms and then use your mass times specific latent heat. So you should have got 33.4 kilojoules. So if you're going to make a revision card on this, I'd suggest these things to add onto your revision card or to write down just at the end of the lesson so you've got the key points of this lesson. The specific latent heat of a substance is the amount of energy required to change the state of 1 kilogram of substance but not change the temperature. When you are heating, and so you are adding energy to a compound, you increase the internal energy, and the energy is used to break them bonds rather than actually raising the temperature, which is why you get this little graph down here, which I've asked you to draw in already. And the specific latent heat of fusion means that you are changing the state from a solid to a liquid. The specific latent heat of vaporization is changing the state from a liquid to a vapor. And then the equation, which you don't have to remember, but you do have to be able to use, is the energy for a change of state is the mass times the specific latent heat. Brilliant work, guys. Well done. Keep up the good work. Go back over the lesson if you need to. You know, this is on YouTube, so you can use it time and time again. And well done.